Okay, question 1 from section 2.A, related rates. Uh, it's titled related rates because we have to relate two different rates, two different things that are changing. We have the radius of a circle that's changing at a certain rate. We need to find the rate of change of the area. So what we're going to do is we need a formula that relates the area to the radius. Area is equal to pi times the radius squared. Now we need to figure out what we know. We know the rate that the radius is increasing with respect to time. That's dr dt. That's equal to 2. We need to find the rate of change of the area when the radius is equal to 3. So the rate of change of the area is equal to dA over dt. It's the derivative of the area with respect to time. This is an implicit differentiation. So now we take the derivative of the right side, 2 pi r dr dt. And we know the value of dr dt is equal to 2. The radius is equal to 3 right here. So the derivative of the area with respect to time is equal to 2 times pi times the radius 3 times the rate at which it's increasing 2. This equals 12 pi inches squared per minute. Question 2, we need to find the rate of change in profit. So we've been given a profit function, okay, but when we take the derivative with respect to time, in this case days, if we take the derivative with respect to time, we're going to also have to know a value of dx dt, the rate at which x is increasing. X is represented by selling x number of units. So here's the rate right here. The sales are increasing at a rate of 10 units per day. X is the rate, or x represents what they're selling, the number of units. So the rate at which it's increasing is dx dt. That's equal to 10. Okay. We need to find the rate and change of the profit when 500 units have been sold. So that's x is equal to 500. So now the derivative of the profit with respect to time, dp dt, is equal to 500 dx dt minus 1/2. Now the 2 as the next one is going to drop down in front and multiply 1/4. 2 times 1/4, where the 1/2 came from. 1/2 x dx dt. Now we can factor out a dx dt from the expression. That's going to leave 500 minus 1/2 x. Now we substitute the values that we know. We know dx dt is equal to 10, so this is going to equal 10 times the quantity 500 minus 1/2 of 500. This is equal to 10 times 250, which is equal to $2,500 per day. That's the rate of change of the profit. So 3.1, lesson 3.1 was using the first derivative as a means of finding intervals which the function is increasing or decreasing. It had to do with the slope of the tangent line. If the first derivative yields positive value, that's a positive slope of a tangent line. That's an increasing interval of the function. And if the first derivative yielded negative values, that was indicative of a decreasing interval. So we take the first derivative, which is equal to 3x squared minus 24x. Okay, now we need to set the first derivative equal to 0 to find critical values. So 0 is equal to 3x times x minus 8, which means the critical values are x equals 0 and x equals 8. Okay, now on a number line we test values in each interval broken. The number line places the critical values on the number line, test points within each interval into the first derivative to see if it yields positive or negative values. So we could test f prime -1, we could test f prime of +1 in this interval right here, and we could test f prime of 9. Okay, it doesn't matter the actual value that it yields, just matters whether it's positive or negative. So if we plug a -1 into the first derivative function, this form of it might be a little bit easier. 3 times -1 is a negative value. -1 minus 8 is another negative value. Negative times a negative is going to yield positive. Okay, now testing f prime evaluated at x equals 1. 3 times 1 is a positive value, but 1 minus 8 is still a negative value. Positive times a negative is a negative. Then f of 9, 3 times 9 is a positive number. 9 minus 8 is another positive number. Positive times a positive, positive. What this means is any number that we would have chosen in this interval plugged into the first derivative function is going to yield a positive value. That means the function is increasing on this interval. Okay? Increasing on the open interval -infinity to 0, and there's another interval right here from 8 to infinity. This region that's negative right here is where the function is decreasing. That means that the tangent lines in that interval are going to have negative slopes because the function is decreasing. So it's decreasing on the interval 0 to 8. Question 4 and 5 actually come from 3.2. I've mislabeled the review. These two are from 3.2. The first derivative test to find relative extrema. This is where the graph has a relative minimum or a maximum. Okay, we find the first derivative, set it equal to 0 to find critical values, and then decide using the first derivative test whether or not they're relative minimums or relative maximums. So the first derivative in this function, if you use a simple power rule here and take the derivative of each of these terms, 4 drops down in front. 4 times 1/4 is 1, so this is x to the third minus 8. If we set that equal to 0, we can add 8 to both sides, and we have 8 is equal to x to the third. Now we can get rid of the power 3 by using the cube root. And the cube root of 8 is equal to 2, so the critical value here is x is equal to 2. Now, this is a critical value. We don't know whether it's a relative minimum or a maximum, so we use the first derivative test. We choose numbers now in each interval plugged into the first derivative, so f prime of 1 we could test, and f prime of 3. Now, if 1's plugged into the first derivative, 1 cubed minus 8 is a negative number, but if 3 is plugged into the first derivative here, 3 cubed minus 8 is a positive number. Now, how we read this graphically is in this interval the function is decreasing, so it may look something like this, where it's decreasing, but when it reaches x equals to 2, then the function starts to increase. Because of that behavior, where it switches from a decreasing to an increasing function, it has to be a relative minimum. So there's a relative minimum when x is equal to 2. Now the actual point that represents that on the graph, we have to plug a 2 as an input into the original function here for both x's. 2 to the 4th power is 16. 1/4 of 16 is 4. 4 minus 8 times 2 is 16. This is 4 minus 16, which is negative 12. So the minimum value is negative 12 when x equals 2. Now question 5, this comes from the same section. These are both from 3.2. It's the same thing, just a different type of function to give us a little more practice here. H prime of x. Now we have to take the derivative of a quotient. We use a quotient rule, which is, if you remember that phrase, low d high minus high d low. So it's the bottom function, x minus 2, times the derivative of the top function, 2x, minus the top function times the derivative of the bottom function, all over the square of the bottom function. simplifying the numerator, we're going to have a 2x squared minus 4x minus x squared over x minus 2 squared. And simplifying one more time, we're going to have x squared minus 4x all over x minus 2 squared. Now, critical values, normally we've been finding them by setting the first derivative equal to 0, and that's still going to work here, but the other part of it is we can also have a critical value when the first derivative is undefined. Because we have a rational equation here, it's going to be undefined at this value when the denominator is equal to when the denominator becomes 0, and to do that we have to have an x value of 2. So there are more critical values than you might think. X equals 2 is a critical value because it makes the expression undefined, or the first derivative undefined. Now we have to find out where the first derivative is equal to 0. Because it's a rational expression, it's only ever going to equal 0 when the numerator here is equal to 0. So there's two values of x that will make the numerator equal to 0. It's x equals 0 and x equals 4. So those are three critical values that we have. So if we test those, 0, 2, 4. So now we need to choose test points within each interval, plug them into the first derivative, see what comes out of that. So we need to test h prime of -1. We could test h prime of +1. We could test h prime of 3 and h prime of 5. We got to figure out what's happening with all these. So if we plug in a -1, -1 squared is positive. -4 times -1 is positive. And a positive, so a positive in the denominator, or in the numerator. Now, this denominator is being squared, so regardless of what happens in the parentheses, squaring it always becomes positive. So the denominator will always yield something positive. Positive divided by a positive is a positive interval. Now, h prime of 1, if we plug a 1 in, 1 squared is positive. -4 times 1, though, makes it negative. So we have a negative divided by something that's always going to be positive down there, so that's a negative interval. Plugging in a 3 for both x's here. 3 squared is 9, but -12 here makes it negative. Negative divided by positive is negative. And if you plug in a 5, 5 squared is 25, but -20 makes it positive. Divided by a positive is positive. So even though we have three critical values, only two of them actually are going to yield a local or relative extreme. And it's when the graph changes from an increasing to decreasing, such as right here, or decreasing to increasing, which is right here. So that critical value and that critical value are actually local extreme. Now, it depends on the behavior of the graph, whether or not it's a local min or a local maximum. So here it's changing from an increasing function, so the function is increasing, but then at x equals 0, it starts to decrease. So that has to be a minimum or a maximum, right? So there's a maximum when x equals 0. Then here, because it's switching from a decreasing function to an increasing function, okay, when x equals 4, we have a minimum. And then we have to plug these values in to the original function here to figure out the point on the graph. So when x equals 0, h of x is equal to 0. So that point is 0 becomes 0. When you plug a 4 into the original function, 4 squared is 16, and 4 minus 2 is 2, 16 over 2 is 8. So the point is 4, 8. Question 6 is also from 3.2. This was labeled incorrectly. That should be a 3.3. It talks about concavity. Anyway, question 6, find the absolute extreme. Okay. This is a similar process, but we now also have to consider the endpoints as being one of the extreme values of this closed interval, not just the critical values. So we have to find the first derivative, set it equal to 0 to find the critical values. So again, using the product, or the quotient property rather, it's the bottom function times the derivative of the top function minus the top function times the derivative of the bottom function all over the bottom function squared. Simplifying in the numerator is going to yield a -2, and then it's all over x minus 2 squared. Now, we can have a critical value, remember, whenever the first derivative is equal to 0, or when it's undefined. It's undefined when x equals 2, and because there are no x values in the numerator, this expression will never equal 0. So the only critical value we have is x equals 2. Okay? But we have to consider the interval on which we want to find extreme values. The critical value does not lie within the interval 3 to 5. So we're not going to consider it as a possibility as giving an extreme value. All that leaves are the two endpoints. So 3 and 5 are going to yield, one of them is going to yield a local minimum, or an absolute minimum. It will yield an absolute maximum. We just have to evaluate them in the function, original function, to see which one has the highest value. If a 3 is plugged into the original function, 3 over 3 minus 2 is 3. Plug in a 5, 5 over 5 minus 2 is 5/3. This one has the highest value. So 3 comma 3 is the absolute maximum in my closed interval. And the 0.5 comma 5/3 is the absolute minimum value. That brings us to 3.3, where we talk about concavity and the second derivative test. They're performed similar to the first derivative test. So in question 7, we start with the first derivative, which we find the second derivative and set that equal to 0 to find points of inflection. Points of inflection are where the graph switches from concave up to concave down, or vice versa. That's the second derivative. If we set this equal to 0 and factor out a 12, and then factor using difference of squares, we can see that the two points of inflection here, or the two x values that make the second derivative equal to 0, are x equals 1 and x equals -1. Well, now this test looks like it's similar to the first derivative test. It is. It's the second derivative test, though. And it describes the concavity of the graph. So we test points within each interval into the second derivative. So we do f double prime of -2, for example, f double prime of 0, and f double prime of 2 to see whether or not we have positive or negative values in the second derivative. So if a -2 is plugged into the second derivative, we have here -2 squared is 4, minus 1 is 3 times 12, that's a positive value. But if 0 is plugged in, 0 squared is 0, minus 1 is negative times 12, it's a negative value. And then here 2 squared is 4 minus 1 is 3 times 12, it's a positive value. Now, in the second derivative test, a positive interval doesn't mean that the graph is increasing. What that means is the graph is concave up, it's curving upwards like this. So the intervals f of x concave up on the interval -infinity to -1, and there's also another interval here, union 1 to infinity. And f of x is concave down on the interval -1 to 1. Okay. Question 8 is a similar thing. We have to discuss the concavity of the graph using the second derivative test, and then we have to actually find the points of inflection. Pretty much the same thing we did. The derivative here is a little bit more tricky. The second derivative is a little trickier to find. It's a product property with a chain rule, a little bit of a chain rule in there. So Start with the first derivative, h prime of x. Now these two are forming a product. Remember the product property. If h of x is the product of two separate functions, f of x times g of x, and the derivative is f prime of x times g of x plus f of x g prime of x. That's the product property. So applying that here, we take the derivative of this first part of the function, which is going to be 3 times x minus 1 squared, and since it's a function within a function, we have to do a chain rule, do the derivative of the inside, which just happens to be 1. And we multiply that by the second function, x minus 5, and then we add the first function times the derivative of the second function. Now, there's a lot happening here, but really we need to consider this as a term added to this as a term. And if we consider both terms and what they have in common, they both have an x minus 1. This one has an x minus 1 cubed, this one has an x minus 1 squared, so they both have at least an x minus 1 squared that can be factored out. So if x minus 1 is factored out from this part of the first derivative, so this x minus 1 was factored out, what that leaves is 3 times quantity x minus 5, which becomes 3x minus 15. Now, from this part, if we factor out x minus 1 squared, that just leaves an x minus 1. Simplifying a little bit inside of that gives us 4x minus 16. That's the first derivative. Now if we do the second derivative, similar technique, we're going to have to do a product property. So the derivative of the first, and then a chain rule, we have to multiply by 1 times just the second function, plus the first function times the derivative of the second. Now if we start to simplify this part of it, 2 times x minus 1 is 2x minus 2, and if we times it by 1, it still stays 2x minus 2. Now if we multiply these two together, we're going to get 8x squared minus 40x plus 32. Now if we multiply these two together, first of all, x minus 1 to the second power is x squared minus 2x plus 1. We multiply that with 4, we get 4x squared minus 8x plus 4. Combining all the like terms, we're now going to have 12x squared minus 48x plus 36. This is the second derivative of h. If we factor out at 12, we have x squared minus 4x plus 3, which factors into x minus 3 times x minus 1, and that means h double prime of x is equal to 0 when x equals 3 and when x equals 1. So those are the points now that we have to place on the number line. To discuss the concavities, we have 1 and 3. Test points in the intervals now. In the second derivative, so we need to do h double prime of 0. We can do h double prime of 2 and h double prime of 4. So when when we plug in a 0 to the second derivative of h, 0 minus 3 is negative, 0 minus 1 is negative, negative times a negative times 12 is positive. 2 minus 3 is negative, but 2 minus 1 is positive. Positive times a negative times 12 is negative, and then 4 minus 3 is positive, 4 minus 1 is positive. Positive times a positive times 12 is positive. We have a region now where we know the graph is going to be concave up here and here. So h of x concave up on the intervals negative infinity to 1 and 3 to infinity, and it's concave down on the interval 1 to 3. Now we know where the graph switches from concave up to down and down to up. We actually need to state the points of inflection, so we know that it's 3 comma something and 1 comma something. So 3 plugged in, 3 minus 1 is 2, 2 cubed is 8. We have an 8. 3 minus 5 is negative 2. 8 times negative 2 is negative 16. If 1 is plugged in, 1 minus 1 is 0. 0 cubed is 0. 0 times anything over there is going to be 0. And these are the points of inflection. Okay, now question 9, second derivative test. Got to pay really close attention. The second derivative test can kind of get mingled with the first derivative test if you're not paying close enough attention. So we start with the first derivative and find the critical values from the first derivative, and we take those and plug them into the second derivative to test the sign of the critical values in the second derivative. So the first derivative is 3x squared minus 10x plus 7. Okay? Doing a little bit of factoring that you hopefully have had a little bit of practice with. 3 times 7 is 21. We need two numbers that multiply 21 to add to negative 10. That's going to be negative 3 and negative 7. So that linear term in the middle splits up into minus 3x minus 7x plus 7. Grouping these first two terms, you can factor out a 3x, so the easier is x minus 1. Grouping the second two, or the last two terms, you can factor out a minus 7. The easier is x minus 1, so it factors into x minus 1. Times 3x minus 7, so the critical values are x equals 1 and x equals 7/3. Excuse me. So the second derivative now is equal to 6x minus 10. If we evaluate the critical numbers into the second derivative, f double prime of 1 is equal to negative 4, and f double prime of 7/3. So it's a little bit harder to find. You take a 6, multiply it by 7/3, subtract 10. 3 goes into 6 twice. 2 times 7 is 14. 14 minus 10 is 4. Now the second derivative says if you take a critical number in the second derivative, it's negative, that means the graph is concave down. So it's a graph that's kind of curved downward, concave down. The critical value then would be the top. That makes it a minimum or a maximum value. So we know there's a maximum value. X equals 1. Now when we plug in 7/3 of the second derivative, turned out to have a positive value, which means the graph is concave up. So that represents a minimum when x equals 7/3. So we're going to have to plug these values in to actually find these points. So if we plug in a 1, 1 cubed is 1, minus 5 times 1 squared is minus 5. That's negative 4, and then we add 7, so that turns into a 3. So 1 comma 3 is the max, relative max. Now if we plug in 7/3, so I plug 7/3 in for x. We're going to get 343 over 27. I need a little more room here. So 343, 27 minus 5, and then 7/3 squared is 39 ninths plus 7 times 7/3. So simplifying this over here, we get 49/3. 5 times 49, let's see, 5 times 50 minus 1, this is 215 minus 5, so that's 245 ninths. This is minus 245 ninths. So to combine all these, we got to get common denominator. So multiply by 9 by 3. So we're going to have 343 27 minus 735 27 plus 441 27. And let's see, 343, we're going to add the 441, so 343, 441, we get 784. Now 784 minus 35 is 49/27. The fractions are not all that bad. Okay, the point of diminishing returns, this was part of 3.3's lesson, the latter part. The point of diminishing returns is a point of inflection of a graph when it switches from concave down to concave up. That means it's still increasing, but just it starts to increase at a slower rate. That's a point of diminishing returns. So what we need to do is find the second derivative of this. I'm just going to simplify this. So this is negative 2/3 x to the third, and then negative 2/3 times negative 12 is going to be positive. 3 goes into 12 4 times 2 is 8, so this is 8x squared, and then 2/3 of 6. How many thirds are there in 6? That's one way you could think about it. Or 3 goes into 6 twice, times 2 is 4, so this is plus 4. So this is what r is equal to. R prime then is negative 2x squared plus 16x. And second derivative is negative 4x plus 16. Now this is going to equal 0 when x is equal to 4. Now first let's just check that's in the specified domain. X can be anything between 0 and 8, where 8 is in thousands. These are in thousands of dollars, so this represents a value of $4,000. Now just to check that this really is a point of diminishing returns, we have to check that the graph is switching from concave down to concave up. So in the second derivative, we can test a 3 and we can test 5. So plugging a 3 into the second derivative, plugging a 3 into the second derivative here, negative 4 times 3 is negative 12 plus 16 is positive. And then 5, negative 4 times 5, negative 20 plus 16 is negative. This is a point of inflection. The graph is switching from a concave up. No, it's a concave down. Sorry, concave up type of a graph and then which is x equals 4, it starts to change to a concave down. So right there in the middle, that's the point of diminishing returns. The rate is increasing much faster than the rate is increasing over here. This has a steeper tangent line than the tangent line on this side. So even though they will still be making more money on by spending more money on advertising, they're not going to be making as much at the same rate as right here, the point of diminishing returns. So spend $4,000. That's the point of diminishing returns. Spend $4,000 on advertising. Okay. So what we're trying to optimize here is the perimeter. So the perimeter formula for a rectangle is 2L plus 2W. Now to optimize or to minimize or maximize any function, we take the derivative. The problem is this is not a function of one variable, this is a function of length and width, which is really going to complicate things. So what we need is a secondary equation. We have some information here that the area, which is length times width, is equal to 225 square meters. So if we divide by one of the dimensions, doesn't matter, we can divide by L on both sides. That yields width in terms of the length. Width is equal to 225 over L, which also means this width right here is equal to 225 over L. So the perimeter function can be written in terms of L, 2L plus 2 times 225 over L, which is 2L plus 550 over L. So the derivative is 2 minus 550 over L squared. Now, if we set this equal to 0, we're going to add this term to the other side. Now there's a couple different ways you could solve this. You could think about this as a fraction. 550 over L squared is equal to 2 over 1. This is what's called the proportion, where we have a fraction that equals a fraction. One way you can solve a proportion is by cross multiplying. So multiply those together and set them equal to each other. We're going to have 2L squared is equal to 550, which means that L squared is equal to 225. You square root both sides, and L is equal to, I mean technically it's plus or minus 15, but because these actually represent lengths and widths of rectangles, we consider the feasible domain, which is positive numbers. So the length is equal to 15. Now we do have to check that this actually is a minimum value here and not a maximum. So using a quick little first derivative test, 15, we test points in each interval on either side of 15. So if we plug in a 14 over here for L, 14 squared is 196. Now 550 divided by 196 is a little bit more than 2. If you take that from 2, you end up with a negative value. So 16 squared, let's see, 16 times 16. Looks like that's going to be 256. Now if you take 550 divided by 256, that's a little bit less than 2. So if you take that from 2, you end up with a positive value. So what this means is the graph is switching from a decreasing function to an increasing function, which proves that this is a minimum. So when the length is 15, we got to go back and find out what the width is. The width is equal to 225 divided by the length, but if the length is 15, 225 divided by 15 is also 15, so the width is equal to 15. So the length and width of a rectangle with minimum perimeter is a square. Okay, so I would recommend drawing this one out. We have an indoor physical fitness room that's a rectangular with semi-circle. Semi means half of a circle on each end. The perimeter, so just measuring around the room like this, if somebody were running around, that's 200-meter running track. Find the dimensions that will make the area of the region as large as possible. So we're maximizing the area of this rectangular region inside. So we can say from here to here, we can say is x, and from here to here, we can say is y. So the area is equal to x times y of that rectangular region. Problem is, if we take the derivative on both sides, we have too many variables on this side. So we need a secondary equation. So it says the perimeter of the room. Now, the perimeter are these two sides of the rectangle. Let me do this in a different color. It's this side of the rectangle and that side of the rectangle. So the perimeter at 200 is equal to 2x, but then it's also this top half and the bottom half. So it's actually a full circumference of a circle. And the diameter of that circle is y. Now the circumference of a circle is pi times the diameter. So we have plus pi times the diameter of y. So this is the perimeter. Now we just need to solve it for one of the variables. If we wanted to solve for x, for example, we could subtract pi y. So we have 200 minus pi y is equal to 2x. And we can divide everything by 2. Now we have area, and now we know what x equals. X equals this value right here. So this is 200 minus pi y all over 2 times y. And this is equal to 200y minus pi y squared all over 2. Now we need to take the derivative. Now this might be easier to do one more little simplify here. If we separate, instead of dividing everything by 2, dividing separately by 2, we have 100y minus pi over 2 y squared. That might be a little bit easier to take the derivative. So a prime is equal to 100y, or 100 rather, minus pi times y. So if we set this equal to 0, that means that 100 equals pi times y divided by pi, and y equals 100 over pi. That's this part right here, 100 over pi. Now, to find x, x right here, if we wanted to again make this maybe a little bit easier, x is equal to 100 minus pi over 2 times y. But we know that y is equal to 100 over pi. Pi's cancel. 100 over 2 is 50. 100 minus 50 is 50. So this has a length of 50 meters. So 50 meters here, 100 over pi meters on that dimension. Okay, question 13. Find the number of units x that produces the minimum. So right here, this means we're going to be optimizing using a derivative somewhere to find use the first derivative test. But what we're minimizing is the average cost. We've been given a cost function. The average cost, c bar, is equal to c over x. So c bar is equal to this whole expression pretty much divided by x, but it's going to make the derivative easier to divide every term separately by x. This becomes 0.2. Now x squared over x is x, and then 10x over x is 10, and 45 over x. Now we take the derivative, we're going to get 0.2 minus 45 over x squared. If we set this equal to 0, so if this were equal to 0 now, I'm going to add this term to the left side. It becomes 45 over x squared equals, now 0.2, I'm going to turn that into a fraction, it's 1/5, because 0.2 means 2/10, which is 1/5. Now, again, this is a proportion, it's two equal fractions, so we can solve by cross multiplying is one technique. We have x squared is equal to 45 times 5, which is 225. Square both sides to get x equals 15. And again, we're only considering the positive. The feasible domain for this problem is x has to be greater than or equal to 0 at least, because you can't produce a negative number of a commodity. So we do have to just show that this is indeed a minimum value. So if we were to take 15 and then we could find c bar prime of 14, for example, and c bar prime of 16, and see what's happening here. So if we plugged in a 14 squared at 45 over 196, if you take that from 0.2, that's going to result in a negative value. C bar prime of 16 would result in a positive value. Excuse me. So it means the graph is decreasing on that interval, but now it's increasing on that interval, so it does indeed, this relative extreme here is a minimum. Okay. And the question was asking, find the number of units x that produces the minimum average cost. It wasn't asking for the actual average cost. So x equals 15 is the answer. Okay, 14 is going to take a lot of work. It's asking what price per unit will yield the maximum revenue. The problem is they didn't give us a price function or a revenue function in here. The revenue is equal to x, the number of units sold, times the price that they were sold for. Okay. Now, this price function I'm talking about here is the demand function. This is what we talked about on Monday, October, or Tuesday, October the 1st. The demand function is lowercase p, and it's a function of x, where x is the number of units. And if we assume that the demand function is linear, that means it's going to be a straight line with a slope. Now the way demand function is set up on a graph is the vertical axis here is the price, and the horizontal axis is the number of units. So the price is represented by lowercase p, number of units is x. So if we try to form ordered pairs from this number, for example, this is an x value because it's the number of units. This is a price value. So we form that into an ordered pair, x comma p, the point becomes 300, comma 40. If we try to form this statement into an ordered pair, price went up $5, that's a price of $45, and they only sold 275 units, so that's 275, 45. Now, the slope between these 2 points is the change in y, which is, if we call this y2 and this one y1, the change in y is -5, divided by the change in x, 300 minus 275 is 25, so that yields a slope of -1/5. Now the price function is linear, so it's of the form y equals mx plus b, so we know the slope is -1/5 x, but we don't know this b value, so we can choose one of the points and use it as x comma p. So p can be replaced with 40, x can be replaced with 300. -1/5 of 300 is -60. If we add 60 to the other side, b is equal to 100, so the price function p, lowercase p, becomes -1/5 x plus 100. Now that we know p, we can plug that in here to find the revenue function. So the revenue is equal to x times -1/5 x plus 100, which is -1/5 x squared plus 100x. Now the derivative is equal to -2/5 x plus 100. If we set that equal to 0, I'm going to add this term to the other side. And end up with that. Multiply both sides by 5. You get 2x equals 500. Divide by 2 and x equals 250. Now we got to be careful on what we have here. Is this an answer? It's the answer to an equation. It's the answer to the question that was asked though. X is the number of units. They're asking what price per unit will yield a maximum total revenue. Now, I guess technically we should just check to make sure this is a maximum value, but if we go back and look at the original revenue function right here, this is a quadratic function with negative leading coefficient, which means it's upside down, so it's an upside down parabola. So the vertex is going to be maximum value. This is the number of units you have to sell to maximize revenue, but what price are you going to sell it? So now we have to refer back to the price function here. Okay, price is equal to -1/5 times the number of being sold plus 100. So -1/5 of 250 is -50. -50 plus 100 means the price needs to be set at $50 to maximize revenue. And at that price, you'll sell 250 according to the demand function. Now, question 15, a little bit easier because the price function has been provided for us. The cost function is there. What price yields the maximum profit? Now, this is an uppercase P. Profit is equal to revenue minus cost. Now, revenue is equal to X times the price. We're here, so that's equal to X. So it's 36 minus 4X, which is -4X squared plus 36X. So the profit is equal to -4X squared minus, or plus 36X minus the cost, which is 2X squared plus 6. So combining like terms, we're going to have a -6X squared plus 36X minus 6. Now to maximize profit, we need to take the first derivative of the profit. So it's going to equal -12x plus 36, which is going to equal 0. Okay, so that equals 0 when equals 0 when x equals 3. This represents the number of units. But again, they're asking which price yields the maximum profit. So they have to sell 3 units to receive maximum profit. What price is that? Well, if we plug a 3 So plug this value into the price function there. 4 times 3 is 12. 12 from 36 is 24. So lowercase p price is $24. Now, what is the average cost? So C bar is equal to C over X. This is equal to 2x squared over X plus 6 over X, which is 2x plus 6 over X. Now we know when the profit is maximized, they're selling 3 units, so the average cost of 3 units is 2 times 3, which is 6, plus 6 over 3, which is 2. That's $8.
Okay, question 16. We have this demand function here, the price in terms of the units sold. 24 divided by, I know it's not real super clear, but it's the square root of x. 24 divided by the square root of x. So find the price that will yield maximum profit. Well, first of all, remember profit is equal to revenue minus cost. We've been given the cost function, don't have a revenue function. So you also need to recall that revenue is equal to x times little p, where p is price. Now, this is going to be x multiplied by 24 over the square root of x. You want to rationalize this. You don't want to have a square root in the bottom of a fraction, so if you multiply it by the square root of x over the square root of x, you get 24 root x over x. But then that x and that x will cancel, so revenue is equal to 24 square root of x. So then profit is equal to revenue minus the cost and then P prime, or the derivative of the profit, is equal to 24. And if you think about the square root of x as x to the 1/2, that's going to be, the derivative of the square root of x is 1/2 x to the negative 1/2. And then the derivative of this is going to be 0.4. I'm going to go ahead and change 0.4 into a decimal. 0.4 is 4/10. 4/10 is 2/5. So that's 2/5. Half of 24 is 12. So the derivative of profit is 12 over the square root of x minus 2/5. Now we have to find the price that will maximize profit. So we need to set the derivative equal to 0 and find the extrema. So if you add 2/5 to the other side, we would get this. You multiply to solve, cross multiply, you're going to get 60 is equal to 2 square roots of x. Divide by 2 and you get the square root of x is equal to 30, so x is equal to 900. That means you have to sell 900 units to realize the maximum profit. The question though is asking for what price would that be. So now we take 900 and plug it back into the price function. And the demand function here, P is equal to 24 divided by the square root of x, and x is 900. Square root of 900 is 30, so it's 24 over 30. That simplifies to 4/5. 4/5 is the same as 8/10, so that's 80 cents.
Asymptote is from 3.6. Vertical asymptotes are found when the denominator is equal to 0. Those are the domain restrictions. Horizontal asymptotes are found by comparing the degree of the numerator to the denominator. So this function in factored form is x minus 2 times x plus 2 in the denominator and x minus 1. So the domain restrictions are x cannot be 2, x cannot be negative 2. Those are the vertical asymptotes. They are the domain restrictions. So vertical asymptotes are x equals 2, x equals negative 2. The horizontal asymptote, if we compare the degree of the numerator, it's at degree 1. The degree of the polynomial in the denominator is degree 2. Now, horizontal asymptotes can happen one of three ways. If the degree in the numerator is smaller than the degree in the denominator, then the horizontal asymptote is line y equals 0. Now, in this problem, we have to factor, this is difference of squares, x minus 4 times x plus 4. Here in the denominator, this is going to factor to a 2x and an x. It looks like we're going to need something like that. So let me go back and show you again the process. 2 times 4 is 8. We need two numbers now that add to 9 that multiply to 8, and that's 8 and 1. So this is 2x squared plus 8x plus x plus 4. So we have 2x factored out, that leaves x plus 4. There's a 1 factored out of that, which leaves x plus 4. So it's x plus 4 times 2x plus 1. A little tricky here on this one. The x plus 4s cancel out, so this isn't actually going to give a vertical asymptote. It's a hole in the graph rather than a vertical asymptote. So now what I wanted to show you here is these have equal degree. It's degree 2 over degree 2. So in that case, you take the ratio of the leading coefficients, which is 1 over 2. So the horizontal asymptote is the ratio of the leading coefficients, which is 1/2 y equals 1/2. Now the denominator, because those canceled, this is the factor that produces a vertical asymptote. So it's x equals negative 1/2 for the vertical asymptote. So the average cost, again, C bar is equal to C over X, which is going to be 0.75 plus 4,000 over X. Now the value of the average function at these two specific X values, for X is equal to 100, we're going to have 0.75 plus 4,000 over 100, which is 40, which equals 40.75. Now, if we go back and take a look at the cost function, they have a pretty small unit cost, per unit cost. It's 75 cents per unit, but they have a pretty large initial cost here of $4,000. So they're not producing very many with X equals 100. And because of such a high initial cost, their average cost is going to be rather high, but as they start to produce more, so for X equals 1,000, Okay, this is 0.75 plus 4,000 divided by 1,000, which is 4. So you can see that dramatically reduces the average cost per unit of producing that commodity. So as they continue to produce more and more and more, the average cost is going to continue to go down, but it's only going to go down up to a certain point. And this is what this was our discussion on limits to infinity. And that's the next question here. Determine the limit of the average cost function as x approaches infinity. So the limit as x approaches infinity of 0.75 plus 4,000 over x. This is equal to the limit as x approaches infinity of 0.75 plus the limit of 4,000 over x. Now the limit of a constant is just that constant. And the limit as x approaches infinity of this, as x continues to get larger and larger and larger, beyond 4,000 to 4 million and 4 trillion, this is going to result in a smaller and smaller and smaller fraction. And as x approaches infinity, this fraction approaches 0. So the limit is 0. 0.75 plus 0 is 0.75. Now, the question asks you to interpret this in the context of the problem. They're obviously not going to be able to produce an infinite number of this, but they're not going to be able to produce or produce enough to get an average cost lower than 75 cents. 75 cents is the limit of how low their average cost can go. That's how you would interpret that. Okay. Last one. The cost for the federal government to seize P% of an illegal drug as it enters the country is modeled by this. P has to be between 0 and 100. Now the way that this is set up, we can use the percent of P as the actual number, because P is between 0 and 100. So we don't actually need to change these to decimals. We can use 25% as the number 25 and 50% as the number 50. So the cost, so for $25, or for 25%, if these federal agents or whatever they are want to seize 25%, then according to this model, it's 250 times 25 all over 100 minus 25, which is 75. And then 25 over 75. If you take a look at this, 25 over 75, there's just 1 over 3. So this is 250 thirds, which is roughly 83, I think it's 83.3. Keep in mind this is in millions of dollars, so if they want to seize 25% of this illegal drug, it's going to cost them a little more than $83 million. Now, if they really up their efforts and are aiming for 50%, that follows the model 250 times 50 over 100 minus 50, which is 50. Now, these two values are going to cancel out, so that's $250 million. So they increase their efforts, they double their efforts, but their costs more than double, up to $250 million. So we're seeing a pattern here. If they increase again, that's going to be 250 times 75 all over 100 minus 75, which is 25. 75 over 25 is 3. 250 times 3 is $750 million. So now, once they go much more than this, 80%, 90%, 91%, 92%, these costs are going to increase similar to an exponential increase. As their efforts are reaching 100% of this illegal drugs to be seized, what's the value of this side going to eventually start to reach? This is another idea of a limit at infinity. So what they're asking is find the limit as C approaches, or as P approaches 100 from the negative side. So the limit as P approaches 100 from the negative side, 250 P over 100 minus P. Now, this is not meant to be done analytically. we've done a numerical analysis kind of here where we've tested some points. If we consider just a rough idea of what this graph might look like, there's a vertical asymptote at 100. All these are 10s. 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. So we have a vertical asymptote at 100. And these represent percentage points of how much of the drug they want to seize. So at 25%, which was about right here, they were at 83 million. At 50%, they were at 250. At 75%, they were way up here. So the costs are going to, as the graph approaches this vertical asymptote of 100, where's the graph heading to? And the answer is it's heading to positive infinity. So the answer to this is infinity. Okay. These first three questions right here come from section 3.8 of the textbook, differentials and marginal analysis. So here in question 1, find the differential. First start by finding dy dx, finding the derivative of the function. I'm going to use a product rule here. Product rule is f prime g plus f g prime. So we start by, we can consider this f and consider that to be the function g. So the derivative of the first function is 2x times the second function, 2x plus 4 squared, plus first function times the derivative of the second function. I'm going to do a little bit of a chain rule here. And this is going to equal, if we wanted to simplify this now a little bit, this is going to equal 4, because a 2 times 2 would be a 4, times 2x plus 4. Now consider what this has in common, what the left side here has in common with the right side. They have a 2x plus 4 here, and a 2 that can factor out. So we're going to factor out a 2 times 2x plus 4. That's going to leave an x times 2x plus 4 plus 2 times x squared plus 3. Now simplifying this in the middle, we're going to have, this is going to be an x squared plus, or rather 2x squared plus 4x. This is another 2x squared plus 6 right there. So we simplify that, we're going to have 4x squared plus 4x plus 6. Okay. Now, this is dy dx. The differential then would just be multiplying both sides by dx. So dy is equal to 2 times 2x plus 4 times 4x squared. Actually, I'm going to think we're going to run out of room. Let's just do it this way. There we go. Multiply both sides by dx to isolate dy. Question 2 starts the same way. We've got to find dy dx. I'm going to rewrite this using rational exponents. So it's raised to the power of 1/3. Well, actually, that would be the original function, 6x squared to the 1/3. So the derivative is equal to 1/3 times 6x squared. Now we have to subtract 1, so we're going to get negative 2/3. and then chain rule 12x. So simplifying this a little bit, let's do over here. We're going to have a 12x in the numerator, and then a 3 times 6x squared to the 2/3. In the denominator, that's dy dx. So dy is then going to equal 12x dx over 3 times 6x squared to the 2/3 power. Okay. Question 3, still from section 3.8. You need to use differentials to approximate the change in revenue. So the change in revenue is actually delta R, but that can be approximated using dr, which is the differential. So we need to start off by finding the derivative of r with respect to x. So we need to find dr dx. That's going to equal 900 minus 2 times 1 x, and then dr is equal to 900 minus 0.2x dx. Now dx is the change in x value. That's equal, x goes from 3,000 to 3,100, then the change is 100 units. The x value we're going to use is the starting value of x right here, 3,000 units. So making substitution, we have dr is equal to 900 minus 0.2 is 1/5, this is 1/5, 3,000 times 100. 1/5 of 3,000 is 600. 600 from 900 is 300, and 300 times 100 is 30,000. And that's $1. So the change in revenue from increasing production to 3,000 units to 3,100 units is $30,000. Okay, question 4. We need to find the derivative of y, so y prime is equal to 4e 3x squared minus 3 times the derivative of the exponent, 6x multiplying, we're going to have y prime is 24x as e to the 3x squared minus 3. Okay, question 5. It's kind of an involved one. This is a quotient rule. So it's low d high minus high d low all over low squared. So start with low, 2x squared plus 6x. Now we have to multiply it by the derivative of the top function. I'm going to take this over here. The derivative of the top function is the derivative of the separate terms of this top function. So this is going to be e to the 4x squared times 8x for the chain rule part, plus the derivative of the second part. So this is equal to 8x times e to the 4x squared plus 4
So that's what we multiply by here. 8xe to the 4x squared plus 4, and minus top function e to the 4x squared plus 4x plus the derivative of the bottom function, which is 4x plus 6. That's all over 2x squared plus 6x. Okay, and then we simplify a little bit. We need to use the FOIL method in both terms here and both terms here. So using the FOIL method, multiplying this term to that term, we're going to get 16x to the third times e to the 4x squared. And then the 2x squared times over here times 4 is plus 8x squared. Now this term times that term there, it's 48x squared e to the 4x squared, and that term times that term is plus 24x. Now we subtract the sum of all those terms. So it's going to be 4x e to the 4x squared. That's that times that. Here we're going to get plus 6e to the 4x squared. Here is 16x squared. And finally we have plus 24x. And remember, all of these terms inside are being subtracted. So the 24x and the 24x would cancel. Only other like terms would be this 8x squared and this minus 16x squared that we would combine. And that's all over 2x squared plus 6x squared. Sorry, I forgot the exponent of 2 up there as well. So combining some of the like terms, we're going to end up with 16x to the third e to the 4x squared. That takes care of that one. We have a plus 48x squared e to the 4x squared. That takes care of that one. Minus 4x e to the 4x squared. Takes care of that one. Plus 6e to the 4x squared. And that is the 8x squared minus 16x squared, which is negative 8x squared. That's all over the denominator with 2x squared plus 6x squared. Okay, question 6. This is a product rule, which is f prime times g plus f times g prime. So this right here is f, this could be g. So f prime is going to be 6, and then we multiply that by g, which is e to the q to the 5th power plus 6q. Now do the derivative of the g function, which is e q to the 5th times 5q to the 4th. This equals 6e q to the 5th plus 30 q to the 5th e q to the 5th. They both have a 6e q to the 5th in common, so if we factor out 6e q to the 5th, that leaves 1 plus 5 q to the 5th, and that's p prime. Okay, question 7. Find the equation of the tangent line using the point. To find the equation of the tangent line, we need the slope of the tangent line. That's going to come from the derivative, so we've got to find y prime. So y prime equals e to the negative 2x plus x squared times the derivative of the exponent 2x minus 2. Now we could spend some time trying to simplify this, but we're only going to use the derivative to find the slope, so might as well leave it how it is. Use the fact that x equals 2, plug a 2 in for all the x's, so the slope, if this x is 2, this 2 times negative 2 is negative 4, plus 2 squared, so that's e to the 0 power. Inside we have 2 times 2, which is 4, 4 minus 2 is 2. So e to the 0 power, anything to the 0 power, is just 1. 1 times 2 is 2. So the slope of the tangent line is going to be 2. Now our equation needs to be of the form y equals mx plus b. The slope goes in place of m. Okay, and now we can use this point as an x and a y value. So 1 equals 2 times 2 plus b. 2 times 2 is 4. Subtract 4 on both sides and we get b is equal to negative 3. So the equation is y equals 2x minus 3. It's the equation of the tangent line. Okay, properties of logarithms. There is a quotient that we can expand using subtraction of 2 logarithms, but we have to take care of this exponent before we can expand the quotient. So the 5, this 5 is going to drop down in front. And then we can expand using subtraction. And now x squared minus 9 is the difference of squares. So, and then we can take this 2 and drop it down in front of that logarithm. So we're going to have 5 times the natural log of x minus 3 times x plus 3 minus 2 times the natural log of x. Now, we're taking the logarithm here, we're taking the logarithm of the product. So this can be expanded further. This is going to be 5, and then natural log of x minus 3 plus the natural log of x plus 3 minus 2 times the natural log of x. And then we can distribute the 5 to each logarithm. So the final answer is 5 times the natural log of x minus 3 plus 5 times the natural log of x plus 3 minus 10 times the natural log of x. Okay, question 9 is doing the opposite of what we just did. Taking multiple logarithms, condensing it down to a single logarithm. So we can start inside, seeing what we have here. This exponent, or this 2 in front of the logarithm, needs to come back up in front as an exponent. Okay, we have a plus sign separating these 2 natural logs, so we can condense the expression x plus 3 and x. We can condense that into a single logarithm using the product property. Now there's a minus sign between 2 logarithms, so we can condense that further into a quotient. And finally, we can take this number in front of a logarithm and move it back up as an exponent. Okay. Question 10, solving this logarithmic equation. For x, we need to isolate the logarithmic term first. So there are a couple options here. A lot of students would like to divide by 3 as a first step, and that
will eventually work. It's might take a few more extra steps. The way I'm thinking of is we can take this -2 and drop it down in front, combine it with that 3 to make -6 times the natural log of x is equal to 12 divided by -6. We have the natural log of x is equal to -2. Now to undo a natural log, the inverse function is a base of e. We're exponentiating both sides using the same base as the natural log, which is base e. Those cancel. So x is equal to e to the -2, which is 1 over e squared. Okay, question 11, we need to isolate the exponential part of this, which is e to the -0.2x. We need to get that by itself, so divide by 300. We have the equation e to the -0.2x is equal to 7/3. Now, we need to solve for x. As long as x is an exponent, we can't solve for it, so we need to cancel the base using natural log. So now we have -0.2x is equal to the natural log 7/3. Divide both sides by -0.2 and we get the solution x equals natural log of 7/3 divided by -0.2. Okay, number 12, find y prime. First of all, we can rewrite, instead of the square root of x squared minus 13, logarithms do much better when you have exponents and not radicals. So we can write this as the natural log of x squared minus 13, the 1/2 power. And then we can bring the 1/2 down in front of the logarithm. So it's 1/2 times the natural log of x squared minus 13. So the derivative of this is going to be 1/2 times 1 over x squared minus 13 times the derivative of the inside function, which is 2x. Okay. Now, simplifying this a little bit, the 2 and that 2 cancel. So we're left with x multiplying the numerator here over the denominator. It's x over x squared minus 13. And that's y prime. Okay, question 13. We need to expand this logarithm into multiple logarithms. It's much easier to take the derivative of separate logarithms rather than this condensed logarithm. So let's rewrite y. First of all, there's a product right there. We can expand that into the natural log of x plus 2 times the natural log of 2x plus 3. Now when we take the derivative, we take the derivative of separate logarithms. The derivative of the first logarithm is just 1 over x. The derivative of the second logarithm is 2 times 1 over 2x plus 3 times the derivative of this inside function, which is 2. So this equals 1 over x plus 4 over 2x plus 3. Okay, question 14, we need to find the derivative using implicit differentiation because this is an equation defined in terms of x and y on the same side. So there's a product here and we can expand this logarithm here. We rewrite this. So this is a product right here, we can expand that. Which we can bring a 2 down in front of that logarithm. This natural log of y equals 7. This is a product right here, so we're going to have to use the product rule. So that's going to be 4y plus 4x dy dx. That's the product rule that stems from this first term. Plus 2 times the derivative of the natural log of x, which is 1 over x, so that's 2 over x. And then the derivative of the natural log of y, we have to do the derivative implicitly, so that's 1 over y dy dx. That's all equal to 0. So now we need to keep the terms on the left side that have dy dx, move the terms that do not have dy dx to the right side. And we're going to factor out dy dx at the same time. So this term and this term would stay on the left side. So this is 4x plus 1 over y. Then you have to minus a 4y on the other side and minus the 2 over x. Now 4x plus 1y, we're going to have to combine that into one single term rather than the sum of two terms. This right here is over 1. In order to add these, we need to have a common denominator, so we need to multiply it by y over y. Adding them together then is going to be 4xy plus 1 all over y. You do the same thing on the right side. To get a common denominator, this needs to be multiplied by x over x. This is going to be negative 4xy minus 2 all over x. Okay. Now we need to isolate dy dx. So we have two options here. We can either divide by this whole entire expression to cancel it out and then divide by it here on the other side. It's kind of tricky to divide fractions like that, so I'm actually going to multiply it by the reciprocal on this side, so times it by y over 4xy plus 1, because that's going to cancel it from there, and then do the same thing over here, multiply by y over 4xy plus 1. So now we can isolate dy dx is equal, if you distribute the y here in the numerator, you're going to get negative 4xy squared minus 2y. And distribute the x down here in the denominator, all over 4x squared y plus x. We need to make an equation in the form y equals c times e to the kt, where c represents an initial population, k is the factor of growth, or the growth factor, t represents time. We do need to find values of c and k. That's our first task. And we know that after 3 days, which is a time value, there are, let me specify that more, that's a time value of 3. There are 200 flies. That's a y value of 200. We know after 5 days, and again that's a value of t equals 5, there are 400 flies. That's a y value of y equals 400. So we can make two separate equations from this information of this form. allowing t to equal 3 and y to equal 200, we can say 200 equals c times e to the 3k. And from this second bit of information, we can say that 400 equals c e to the 5k. Now taking this top equation we've made here, we can solve it for c by dividing both sides by e to the 3k. So c equals 200 over e to the 3k. Now we can take that value and plug it in there for that c and get the equation 400 equals 200 over e to the 3k times e to the 5k. And now these terms can reduce to e to the 2k. So we get the equation 400 equals 200 times e to the 2k. Divide both sides by 200 and you get the equation 2 equals e to the 2k. And if you take the natural log on both sides, it cancels a base of e. So from that we get that the natural log of 2 is equal to 2k, and from that, dividing both sides by 2 to isolate k, we get k is equal to the natural log of 2 over 2. Now, we had solved for c previously up here. We knew the value of c was 200 over e to the 3k, but we did not know the value of k. But now we do. So we can continue this now and say that c is equal to 200 over e to the 3. Now multiply this by the value of k, which is natural log of 2 over 2. This is 3 times the natural log of 2 over 2. Since these are multiplying and we're dividing, we can actually move this dividing by 2 to divide the 3 by 2. And the reason for doing that is if you have a number in front of a logarithm that's multiplying a logarithm, then you can move that number as an exponent. And now we have e to the natural log of 2 to the 3 halves. E to the natural log are inverses of each other, so those cancel out. So your value of c is 200 over 2 to the 3 halves. So we know the value of k, and we know the value of c. We can finish our model. Y equals 200 over 2 to the 3 halves times e, the natural log of 2 over 2 times t. And the value in finding a model to fit that data is, in addition to knowing how many flies there are after 3 days and 5 days, we can now find how many flies there would be on any number of days by plugging in different values for t. We can make predictions further on down the road in terms of days and weeks and months by using this model.
Alright, last question. A little bit of a twist here. This time the demand function isn't linear. The demand function here, p equals ce to the kx, the demand function is exponential. We've been dealing with linear models for demand where increasing the price means that less is sold following a linear model. And it's true here, increasing the price. So when it was $4, you sold 400 units. When it's $5, you only sold 300 units. So increasing the price dropped the demand, less units were sold, or fewer units were sold. But this is not going to be modeled with a linear function. It's going to be modeled with an exponential function. So it's almost, actually it is the same situation we had in the problem involving the fruit flies. We have two things we don't know. We don't know an initial C value, and we don't know the growth factor, the relative growth factor K. So it's pretty much a repeat of the same problem, just a new scenario. So when the price is $5, 300 units sold, and the price dropped to $4, then 400 units were sold. So we take this top one here and solve it for C. We're going to have C equals 5 divided by E to the 300K. So we take this value now and plug it into that C. We're going to have the equation 4 equals 5 divided by E to the 300K times E to the 400K. So if you consider those two values, E to the 400K divided by E to the 300K, they're exponential expressions that have the same base, and so you subtract the exponent. So this leaves us the equation 4 equals E, 5E rather, to the 100K. Divided by 5, because now what we're solving for is K. K is a variable that's in an exponent. We can't solve for that as long as it's an exponent, so we got to cancel the base. We have to isolate the base first, so divide by 5. And we get the equation 4/5 equals E to the 100K. Take a natural log on both sides. We have the natural log of 4/5 equals 100K. Divide by 100 and get K is equal to the natural log of 4/5 over 100. So we take this value and plug it right in here for K in order to find the value of C. So now C is equal to 5 divided by E to the 300. And then I'm going to make one slight change over here before I substitute this in. Natural log of 4/5 divided by 100 could be thought of as 1/100 times the natural log of 4/5. Thinking of it that way is going to make this computation here a little bit easier. So this is going to be 1/100 times the natural log of 4/5. Okay. So 3 multiplied by 1/100, or 300 rather, multiplied by 1/100 is just 3. So we have 5 for E, and then 3 times the natural log of 4/5. Now this 3 in front of a natural log was initially, or could be brought up back up as an exponent. So we have 5 divided by E, the natural log of 4/5 to the 3rd power. Now we can cancel the E and the exponent of natural log, and we're just left with E, or 5 divided by 4 cubed is 64, 5 cubed is 125, and that simplifies to 625 over 64. So the directions of the problem just told us to solve for C and K, so there's C and there's K right there, or right here rather.